Okay, number 47 says to sketch the graph of y equals 1 minus 2x over the quantity of 4x minus 7. To do this, you first have to find out what your vertical asymptote is. So your vertical asymptote is whenever the denominator is equal to 0. So we have 4x minus 7 equal to 0, so x equals 7 fourths. So we would, at 7 fourths, put a little vertical line. That means that the function can never cross this vertical line, because otherwise then you would have division by 0. As the function approaches this vertical line, we have smaller and smaller quantities in the denominator, so it either shoots up toward positive infinity or it shoots down towards negative infinity. And figuring out whether or not it shoots up or down will determine what the function looks like. So we also need to figure out when the function is 0. So it is 0 whenever our numerator is equal to 0, and that is at x equal to 1/2. That means that there is only one place where it ever crosses the x-axis, and that is right here. So then we can figure out the sign of the function to get a rough estimate of how the function looks. So when x is less than 1/2, I have 1 minus 2 times something less than 1/2, right? So 1 minus 2 times, but 2 times 1/2 is going to be 1. So it is actually going to be, or less than 1, so it is actually always going to be positive, right, at x less than 1/2. On the bottom, right, when you think about it, we can find that x is always, or excuse me, 4x minus 7 is always going to be negative 4x less than 1/2. Between x equals 1/2 and x equals 7 over 4, the numerator will always be negative, and the denominator will always be negative. So a negative over a negative gives us a positive, which gives us what our function looks like between 1/2 and 7 fourths. Past 7 fourths, 1 minus or above 7 fourths for x greater than 7 fourths. 1 minus 2 times something greater than 7 fourths always ends up being negative. And 4x minus 7 for x greater than 7 fourths always ends up being positive. So a negative over a positive gives us a negative, which means that it must shoot downwards towards infinity as x gets closer to 7 fourths. And as x gets more positive, 4x minus 7 grows faster than 1 minus 2x, so it will eventually try to hug the x-axis and get smaller and smaller and smaller. Okay, and that is number 47. In number 48, we have express the quotient function y equals x plus 6 over x minus 1 in the form y equals a over x minus 1 plus b. So really that's the same thing as what we had seen in the previous problem, number 40, only much easier. The reason for that is that if we, well, no, I don't want to really express it that way. I mean, all we have to do is really just use long division of polynomials, right? Where x minus 1 is our denominator and x plus 6 is our numerator, so we throw them into the long division algorithm. So 1 times x gives us x. 1 then times 1 gives us negative 1. Subtract these two together, we get out when x minus x is 0. 6 minus a negative 1 is 7, right? So we have y equal to, one moment, something froze here. I slowed down there a little bit because I'm not used to actually seeing it this way. We have 7 over x minus 1 plus 1, where 7 is our remainder when we divide x plus 6 by x minus 1. Okay, number 49. Let's see. I don't have a lot of work there, so it must be pretty easy. State the domain of the function f of x when it is equal to 3 over x plus 2. Well, that's actually really easy. We can just see that we have to know that we cannot divide by 0 and still get out a real number, so x can never be equal to negative 2. Another way of saying that is that the domain is all real numbers except for 2. To find the domain of number 50, we have to factor x squared minus 5x minus 14 so that we can know when it is equal to 0. And its factorization is x plus 2 times the quantity of x minus 7. So we could say, in a very similar sense to number 49, that it is all real numbers except for negative 2 and 7. Number 52... Sketch. That's right. I did this in the wrong order. All right, so we'll do number 51 first here. We know that we can never take the square root of a negative number and still get out a real number. We would get out a complex number, but we'd never get out a real number. And we want to find the domain where we get out all real numbers. So we need to figure out when x plus 3 is greater than or equal to 0, and that will be valid values of x, and that is whenever x is greater than negative 3. So our domain is all numbers which are greater than or equal to negative 3. Right? So starting off with negative 3 and all numbers greater than that. Going down to number 53. Number 50... Oh, nope. I'm sorry, that's right. Let's not skip it. Number 52. So for x less than negative 2, we plot x minus 1, right? So x minus 1 is the same thing as the function that looks like this. Right? We would know how to plot that linear function, right? But we would only plot it starting from, this should actually be moved over a little bit to right here, right? So I'm incorrect right there. It should look like the linear function, and it should start right here. It looks like this, right? But we only want to plot, let's see, medium eraser. We only want to plot up to that point of x equal to negative 2. Between negative 2 and 1, we want to plot the function x squared, right? So the function x squared looks like this, roughly. But we only plot it between negative 2 and 1. Right? It's piecewise. For x greater than 1, we plot the function 3 minus x. Nice linear function. We know how to do that. Right? But we, again, only plot it for x greater than 1. Okay. And that's number 52. Why don't we start off at number 53 in a new video.